Hey, I'll be explaining permutation shift problem from Harvest's contest. Okay, so an identity permutation of length n is an array 1, 2, 3 till n. So it's just a of I equal to I. Okay, we perform the following operations to an identity permutation of length n. Okay, firstly we cyclically shifted it to the right by k positions where k is unknown to you. Okay, and secondly we perform the following operation at most m times. So pick any two numbers of the array and swap them. Okay, so you are given the values of n, m, and the resulting array. Your task is to find all possible value of k in the cyclic shift operation. So basically, we are given, let's suppose we have any identity permutation. Let's suppose n is 4, and what we are doing is we are cyclically shifting it to the right by k. Let's suppose our k was 2. So after two cyclic shift operations, our resulting array will be this. And secondly, what we are doing is swapping any two elements m time. So let's suppose our m was 1, just 1. So we can swap any two element. Let's suppose we are swapping these two. Then our resulting permutation will be 3, 1, 4, 2. So basically, we are given the resulting array, and also we are given that we can perform at most m operations. M swapping operations, and we need to find all the values of k's for which we can reach the resulting array from the identity permutation. Okay, yes, that's the question problem. Okay, so let's look at the sample. Okay, so our n is 4 here and m is 1, and our resulting array is 2, 3, 1, 4. Okay, so what we are doing is okay, and the answer for this is there only exists one k and that's equal to 3. So first of all, let's try to make identity permutation from the resulting array instead of doing doing it in other way. So for this, we'll just cyclically shift the resulting array to the left instead of right by k. So we are just reversing the process, and for the swapping, it doesn't matter. So yes, let's. Okay, so answer is 3. So our k is 3. So let's just shift this resulting array to the left by 3. So our permutation will be 4, then 4, 2, 3, and 1. And also we are given that we can perform m equal to 1, and we can perform at most one operation to make to try to make the identity permutation. So here what we can do is swap these two elements, and yes, we can reach the identity permutation when k is 3 and our m is uh, 1. Like we can perform at most one operation, and here we are only performing one swapping operation. Let's check if when k was 2, why answer is not possible. So we have to, first of all, we have 2, 3, 1, 4. Now shift this resulting array to the left by 2, then our permutation is 4, 1, 4, 2, 3. So here the most optimal way to uh, get the identity permutation is swap these two elements, and after that swap these two elements. Like let's suppose, first of all, suppose we are performing first operation. So after swapping these two elements, we'll reach sorry, we'll reach this permutation, and after swapping these two elements, we are reaching uh, the identity permutation. Now there's no way we can do this in only a single operation, swapping operation, and we are requiring at least two swapping operation to reach the identity permutation. So which is greater than m. So for this case, answer is not possible. Okay, so yes, that's this is the problem. Now let's look at the approach for this. First of all, one thing to notice is let's just forget about the cyclically shifting part for now. And let's suppose we have some array 2, 3, 1, 4. Let's just forget about that cyclically shifting part. So now our problem reduced to, we are given an array and we need to perform uh, minimum number of swapping operations. Why minimum? Because like we can just perform at most m swapping operation. That's why. So now we are given an array and we need to perform minimum number of swapping operations to it such that we can reach the our desired permutation. So this is a kind of standard problem. So in this in this type of problem, what we do is like think it as a graph, or like connect the sorry think it as a graph and just try to make all the values to its desired position. So in this case, to make the identity permutation, 2 needs to be at the second place, 1 needs to be at the first place, and 3 needs to be at this place, and 4 is on its position, so it doesn't matter. So here what we do is now our uh, like permutation is divided into like multiple connected components. In this connected component, like multiple cycles we can say. So in this cycle is like this, and it's just self loop here. So here we can just swap. Let's get answer for this cycle. So what we can do is just swap the adjacent elements. So we had 2, 3, 1 like this. So by swapping these two elements, now 2 is at its desired position. 2 is here. 3 is still not at its desired position, and 1 is still not at its desired position. So 2 is sorted now after one swap. After one swap, 2 is sorted, but still 3 needs to be here and 1 needs to be here. So will just require one more operation, and both of them are at its desired position. So looking it in the array, it will look like 2, 3, 1, 4. Swap these two elements. Now our array is like this. Now swap these two elements. Our array will be like this. And see, we reach the desired permutation in two operations. So one thing to notice is for each cycle it will happen like this. So here the cycle size was 3. So we require two operations. Like so, for any cycle of length x, will require x minus swapping operations no, to reach the desired permutation, and we'll have such multiple x y z multiple cycles, and for each cycle we require its size minus 1 operations. and total operation will be also the x plus y plus z, and or it just sum of all total elements, which is n minus number of cycles. C is number of hours. Okay, let's just leave it. C is just number of cycles. So yes, these are the number of operation will require, minimum number of operation will require to reach the identity permutation from the given permutation. So yes, just a second. Okay, so now we have solved this sub problem. Now also, let's suppose there was no one thing note. Let's suppose there was no self loop in our permutation. Like it was like something is connected to this, or maybe wait a minute, maybe this, these two. Like it's just the case where there are no solid loops. In such case, uh, the best thing is to okay. So from this equation, to minimize the total operations, we can see that if we maximize total number of cycles, then our operation will be minimized. So for this case, and also here in this case, there are no self loops. So the best way to the best case will be that when uh, like cycle size is 2 for each and every connected component, each and like each and every connected component or cycle has its size is equal to 2. So in this case, when we this is the case when we are ignoring that self loop part. So this is the best case for maximizing the cycles. So total operation in this case will be, now we know that cycles are n by 2. Why? Because we are pairing two elements. So our operation is n minus c. Total number of operation is n minus n by 2. So we'll require n by 2 swapping operations to, in this case, to reach the identity permutation. And let's look at the m constraint for m. But m here is less than or equal to n by 3. So now we can see that some of the it is necessary for some of the elements to have the self loop. Like self loop means that they are at its desired position uh, in that identity permutation. So like they have the same position in the resulting permutation and identity permutation. So this is telling us that will require some x amount. Let's suppose will require some x amount of self loops such such that our total number of operation will become less than or equal to n by 3. So by this we can see that okay, total operation is n minus cycles. So uh, total operation is n by 3. The given condition is n by 3 is greater than or equal to n minus cycles. Now cycles is just okay. Let's suppose we have x amount of self loops. So our cycles will be x plus uh, x plus, now remaining elements are n minus x, and for all the remaining elements, like these are the self loop, and for all these remaining elements we can just pair up Na2 element to maximize the cycle count. So in this case, we'll require n minus x by 2 swapping operations, sorry, n minus x by 2 pairs, or n minus x by 2 number of cycles. So these are the total cycles we'll be having, and this condition should be satisfied. Now let's solve this equation. I just move whole thing to here. So now it's x plus n minus x by 2 greater than or equal to, and move this thing to here. So it's just n minus n by 3. So after this, 2x plus n minus x by 2 is greater than or equal to 2n by 3. So 4n by uh, okay, 4n by 3 is greater than equal to x plus n. So now move this and this side. So x should be greater than or equal to 4n by 3 minus n, which is x should be greater than or equal to n by 3. So this tells us that we should have at least n by 3 elements which will be at its desired position in the given array, and like it just we need n by 3 such elements which for which a of I equal to I in the resulting array, such that this will tell us that okay, we in this condition we can it is possible for us to perform m swapping operations, at most m swapping operations, and reach our desired uh, identity permutation. So now from this we got to know that okay, we'll require at least n by 3 elements at its desired position. Now let's look at that cyclically shifting part. So it's just that for some k, let's suppose we shifted the given resulting permutation to the left by any k. Now in this case, it should be, this condition should hold, like at least n by 3 elements should be at its desired position. So let's suppose we had n by 3 these given n by 3 elements at its given position, and we just need to check for this k that if total number of operation will require is less than or equal to n by 3 or not. Like first of all we'll check if for this given cyclic shift, uh, does there exist at least n by 3 elements which are already at its desired position in the identity permutation. So yes, now if for this uh, if for this cyclic shift this condition is holding, that means that n by 3 elements, now these given n by 3 elements will not be at its given position, desired position, in other in some other cyclic shift. Let's suppose k2, and let's suppose this is k1. So it is guaranteed that if they are at its desired position uh, for this k1, then they'll definitely will not be at its desired position for this for any other cyclic shift. So now for this k2, let's suppose we have another n by 3 elements at its desired position, then they'll not occur for any k3, and for this k3 we have another n by 3 elements which are at its desired position. Now all the elements are covered in this. So because ny. So this tells us that we will require at most uh, three cyclic shift at most three distinct cyclic shifts, such that our answer is just total number of cyclic shifts for which the given condition hold is at most three, because all the if for any of the cyclic shift we are getting the desired permutation, then those elements are removed from the our consideration part for other cyclic shift, and those are removed for other cyclic shift, and it is just we just require 3 into n by 3. This is just a cyclic shift. This 3 is the total cyclic shift, and for each cyclic shift, the best case is when we have at least at least n by 3 elements at its desired position. So yes, our answer total number of distinct cyclic shift will be at most 3 only. So what we can do is what we can do is for each of the cyclic shift, we we can check optimally that if uh, total number of after cyclically shifting the given array by k, resulting array by k to the left, we can just check that how many number of elements are at its desired position. By desired position, I mean that a of I equal to I, v of I equal to I after the cyclic shift. How many elements are at its desired position after k number of cyclic shifts, and those are greater than if those are equal greater than or equal to if those are greater than or equal to n by 3, we'll just we can just simply check answer for that total number of operation will require for that particular k, and such case which uh, whom this condition will follow are at most 3. So will just require 3 number of checking conditions. So we can we can write the algorithm of checking condition in O of n, and it's fine for us in that way, because and for calculating the calculating this for that particular cyclic shift minimum number of operation required, what we can do is we can use maybe disjoint set union or just a simple DFS to just to mark the connected distinct connected components, total number of connected components, and we know that our total number of operation is n minus total number of cycles or connected components. So what we can do is we can use DSU to check the total number of connected components, and if this value is so less than or equal to m, then yes, for this particular k answer our answer is possible. So we'll just push it into our final answer array. So yes, this is the whole approach. Let's look at the code. Okay, so this is my template for DSU. I'm just marking that connected component. Okay, okay, we have an array. We are inputting an array. Let's go. Okay, we are inputting an array, and this pose array tells us that uh, how let's suppose we have any element x in our resulting array. So it just telling us that how many cyclic shift It's behind from how many cyclic shift to the left, it's behind from its desired position. So let's suppose 1 2 let's suppose it was like something like 1 2 4, something like this. So for this one, what I'm storing is its desired position is 1, right? And its current position is 3. So what I'm storing is I its current position minus its desired position, like total left, it just total number of left shift operation will require. So it just 3 minus 1, which is equal to 2. So this tells us that will require two left shift operation to make uh, this current element at its desired position. So yes, what I'm doing is now storing for all the left cyclic shift operations for all the elements. I'm storing the frequency of uh, number of cyclic to, like what's the k number of cyclic shift will require for this current element to its desired position, and for each of those cyclic shift operations I'm counting the total number of elements which will be at its desired position after those amount of cyclic shift operations. So yes, this is just a frequency. This is to check if the for the given array our elements are less than sorry, total number of cycles n minus total number of cycles is less than or equal to n by 3 or not. So yes, okay, we have set of answer like to store distinct answer, and now this condition is the same which I mentioned before. uh, Post means that total number of elements which are at its desired position after I number of cyclic shifts. So n minus it just x. Let's pose of I equal to x. So see now we know that operation equal to n minus this and x plus n minus x by 2. So it just the give the equation which I mentioned before, like these number of element. It just this tells us that total number of cycles or connected component in my given array. So yeah, and if this value is greater than or equal, sorry, greater than m, then I can skip checking for this part. And now this will guarantee that we'll only check for at most 3 k values of k. And if this condition is satisfied, we can just use DSU or DFS and anything to mark the connected components. Here what I'm doing is our target. Now this target is element which sorry, position of the element which we are currently on, and moving that element to the left by I. Okay, let's suppose it's something like this by I. Now this element is moved to this position. Let's suppose we had x here. Now it's moved to here, and just now target tells us that position of that particular element after I amount of left shift. So now this has moved to here. So now it's here, and after doing this for all the elements, for this we know that index of this is target, and this target element at this index target should be at index x for identity permutation. So what I'm doing is just making an edge from current index target t to a desired index x. So this is how I'm making the connected components like this, something like this. Yes. So after marking all the connected components, and this is just to check total number of distinct connected components in my array after I number of cyclic shifts. And now this condition is to check if the uh, total number of operation n minus total number of cycles is less than or equal to m or not. If it's less than or equal to m, we can just insert the current answer to our final array. Uh, Mark it current cyclic shift as a final answer. So, and it is guaranteed that size of the answer will be less than or equal to 3. So yes, this was the explanation for this given problem. Thanks.